So our next speaker is Dr. Adam Woods. Dr. Woods is Associate Dean for Research in the College of Public Health and Health Professions at the University of Florida. He's also co-director of the Center for Cognitive Aging and Memory in the McKnight Brain Institute. Dr. Woods' overall research program focuses on discovery and application of novel, non-invasive interventions for enhancing cognitive function in adults with and without neurodegenerative disease, and he's a national leader in the field of neuromodulation. Today, he will be talking about leveraging artificial intelligence, clinical trials, and neuroimaging to precision dose transcranial direct current stimulation.
I wanted to thank the organizers for the opportunity to come and talk to you today. I'm going to talk to you about and take you down a path of work we've been doing over the last 4 or 5 years, trying to really leverage individual variabilities to customize treatment options for promising technologies, specifically in the neuromodulation space. So I'll talk to you about transcranial direct current stimulation today. I'll also talk to you about data from neuroimaging, specifically from magnetic resonance imaging. And we're going to talk about some of the AI methods that we've heard about in other speakers' talks and how we're leveraging these different modalities and information in the context of clinical trials that we have run in the past and are running at present to really try to precision dose a technology that we think has quite a bit of promise. Yes. In the everyday world. I will argue that we are not necessarily there yet for everyday world, but we are working towards this technology being applicable in a much broader context. So how many people have heard of transcranial direct current stimulation? Wow, this is a great audience. A lot of times I get blank stares. 10 years ago, no one would have raised their hand. So this is a transcranial electrical stimulation technique that involves the application of a weak electrical current, typically in a majority of the literature between 1 and 2 milliamps. But now we see the field pushing up to 5 and 6 milliamps. This has been in the 1-2 milliamp range, not because of safety, but really because of tolerability for stimulation of the scalp. Regardless, this generates a static DC electric field that alters the resting membrane potential of the underlying neurons. An important caveat, this is not transcranial magnetic stimulation, so we're not generating action potentials, we're altering the resting membrane potential to either increase or decrease the probability of firing of the stimulated neurons, with the ultimate goal of enhancing the neuroplastic response of tissue. 12, 13, 14 years ago, when I first came into contact with this technology, the reason I was excited was because of its safety profile, its potential ease of application, and the fact that if we could interface directly with neuroplasticity, it had a wide potential list of applications that could have meaning for a wide variety of populations. Now, why TDCS in the everyday world? Well, in this, I will say, and it's important to note that there are no, at least in the United States, clinically or FDA-approved applications of TDCS at present. In other locations in the world, there are approved applications for depression and a variety of other approaches. This is a technology that has not been fully realized in terms of its potential as of yet. I'm going to talk to you today about one of the reasons I think we haven't realized its potential and how I think we can get there, at least one version. Now, why could this be applicable to the everyday world? Well, it turns out over the last 10 years, there's been a lot of work and development to improve this low-cost technology for application with rigor in the home. Using either remotely supervised or other methodologies, this technique can be applied in very similar fashions that we would do in the clinic or in the lab with a remote supervision WebEx interface and a custom designed device that companies are now selling that allow for fairly high fidelity application. That means the actual potential deployment for this could be very easy. Because of its cost, it can be very accessible. It means we can push potential clinical interventions into rural spaces that we otherwise may not have access to. None of this is fully realized as of yet. It's where we would like to go, but we have work to do to get there. So what are some of the things, and I stress some, of the things standing in our way of really realizing the potential of this technology? Well, the approach for TDCS or actually the literature, if you look across, in many ways has shown quite a bit of variability. And stepping back for just a second, this over here to the side is from one of our recent papers doing a meta-analysis within the field of cognitive aging and TDCS applications. And ultimately what it shows is promise for moving the needle on cognitive function in terms of domains that change as we get older. And this is true in many spaces of cognition, but also in terms of depression, anxiety, and other domains. However, there's a lot of variability in treatment response. There are entire large trials that have failed at group level analyses that have not shown these large effects. Yet, when we dig down into these data, we see classes of responders that meet what we would define and the FDA would define as clinically meaningful change. Yet we have not shifted our field to actually leverage that information. In fact, TDCS uses one of the most archaic approaches to dosing I've ever seen. Everyone gets exactly the same dose. Now imagine if we took a blood pressure medication and we said, irrespective of your metabolic panel, irrespective of your weight, irrespective of level of disease, everyone gets the same dose. Half your patients are dead or really have crazy levels of hypertension uncontrolled. So in TDCS, we've kind of taken that approach. 2 milliamps at this location, that is all, magic will happen. Wrong. Magic does not happen. Magic may happen for a few people, but not the group. And so we've ignored this and we've used a one-dose-fits-all approach. Well, gee, there's all sorts of variability. The amount of fatty tissue on the head, the actual individual variability in the actual neuroanatomy itself, and a variety of other features that are even beyond anatomical. Individual differences are one of the beauties of humanity. We're all our own little unique fingerprints. Why not leverage that information to adjust how we're treating these participants and patients? Well, just using aging and using anatomy as an example, these are some papers that really just reiterate points that have been known for decades upon decades, and that is to say that not all areas in the brain atrophy at the same rate as we get older, and that the different tissue types, there's quite a bit of variability in how they change as a function of age. And so even just using age as an example, we see quite a bit of variability decade to decade to decade. But then let's move beyond that. Let's just talk about the base individual variability that each person in this room exhibits at a brain-specific level. More and less gray matter, more and less CSF, more and less, et cetera, et cetera. Now, why does that matter? At its base, TDCS is applying electric current to the scalp through 2 or more electrodes. Even taking the most simple approach of 2 electrodes, that current has to pass through the skin, the adipose tissue, the skull, the gray matter, the white matter, the CSF to distribute current within the brain. And all those individual differences matter because each of those tissue types have different levels of conductivity. And the number one rule of electricity is electricity takes the path of least resistance. So every person will get a slightly different, although similar, pattern of stimulation. Now, what's great is there are some tools, and now freely available tools, that allow us to take someone's T1 weighted MRI and actually create a very accurate model, a finite element model, of where the current is likely to go when injected at one point and taken out at the other. Well, we know where we put the electrodes roughly. And then if we know what the brain looks like, we can segment that out and using, and this is a simplification in many ways, using a basic computational modeling pipeline for finite element modeling, you hypersegment the T1. A lot of this is very automated these days. For high fidelity models, there's still some manual interface that is necessary to correct any errors in the automated segmentation. But with deep learning and other approaches, the segmentation is getting incredibly accurate versus the old days. It would take 6 weeks to segment and model one brain. Now we are down to a matter of typically minutes on well-equipped systems. Regardless, once you have those different tissues and you basically know the rough estimate or the literature-based estimate of conductivity for each tissue, you can volume mesh, finite element simulate, and then create ultimately what we think of as current density maps. These current density maps are not fMRI. What the red means, the more intense red means, more current is estimated at that voxel location, whereas going into the deep blue, you will see that this is where current is not predicted to actually take place or occur in that location. You can also get directional information of current flow between the electrodes. And the beauty of this, experiments by Alex Opitz and many others have actually demonstrated literally in the human brain that these models are producing very accurate results. So here's just a quick example of an aging study. This is the largest finite element modeling study of this type to date, done by one of my former postdocs who's now faculty at the University of Florida, Dr. Aprinda Indalastari. And in this, we were simply modeling decade to decade the differences in electrical current distribution that were occurring as a function of atrophy within the brain. And as you could see, one factor, in this case, only about 9 or 10% of the variance, to be honest, of the total sample, but still a factor that produces and accounts for an amount of variability in what we see when applying current at the same location with exactly the same current. So that fixed dosing mentality produces different profiles of current. More importantly, here's an example of 15 specific brains that were modeled out that had the same application at F3 and F4 over the frontal lobes at 2 milliamps. And you to the eye can look across these and see the various differences brain to brain in these profiles. And so this is just to prove the point that there are, in fact, a wide array of individual differences. So can we use this? If we know where we think the current went with these high fidelity models, does it actually predict the impact of TDCS or how TDCS impacts the brain and behavior? And that was an outstanding question. Now, to address this, we leveraged some old data on a paper we had published back in 2019, where we had done an in-scanner study where we applied TDCS in scanner, and we had them doing an in-back task, which you heard about earlier today. Thank you for that. And we had them do that in-back before stimulation, during stimulation, and after stimulation. And then we had them go through an active versus a sham set of conditions. They were counterbalanced and blinded in both cases. And we tried to investigate in this context how we can impact a well-functioning working memory network. We trained them to criterion, at least 80% performance on the in-back task before we put them into the scanner. Because rather than having all the flux of improving performance, et cetera, we wanted relatively stable performance. And we wanted to see how we could perturb mechanistically the functional network, or in this case, functional connectivity within the working memory network. And what we found was this very specific increase in functional connectivity during active stimulation, but not sham, between left DLPFC and left VLPFC. Stepping forward and modeling each of those individuals with the 10 tissue type segmentation to generate their current distributions, what did we find? Well, we created these models individually for all 15 participants. These are the current density maps for each of those 15 participants. And then what we did was we extracted the exact same ROIs in left DLPFC and VLPFC and extracted the beta values from functional connectivity, in this case, during stimulation that we had shown to be changed. And then we compared that to the median and the max current density in those exact same regions. And what we found was that left DLPFC, but not left VLPFC, was significantly associated. That meaning the current injected into DLPFC was what was driving the overall change we had seen in functional connectivity. But the current increase that occurred in left VLPFC did not. This gave us some very interesting mechanistic insight. But more importantly, for the purposes of this talk, it actually told us that these current models could have value in predicting how TDCS would impact the brain. Now, can we leverage this? Can we use this information? And more importantly, does this actually predict impact of TDCS on behavior? Because ultimately, that's what we're trying to change. Well, this is where we dove in and went beyond a simple ROI-specific analysis. While we could do that, behavior is far more complex than any single ROI. And what we want to look at, because we have this mass multivariate data set where we have voxel-wise current intensity, voxel-wise direction of current flow, and then we have our behavioral outcomes, what have you, from these various trials we've run. We wanted to actually leverage artificial intelligence, in this case, machine learning, to go after this multivariate data structure and use machine learning what it's best for, which is pattern recognition in these complex and dense data structures. The reality is if we knew exactly where to look in the brain and we knew that exactly this was the mechanism underlying, we may not need a method like this. However, we know very little. And I think this point was made by Joy the other day, which is we know exactly this much in this context. It's the same thing for this field as well. It means job security for us investigating it, and it means lots of fun questions still to ask. So we leveraged another trial we had completed, and this was one where we had two groups that underwent 2 weeks of cognitive training paired with TDCS, all older adults. And in this study, which we published in 2019, we had found a significant improvement in in-back performance in the active but not the sham group. So this is only 14 individuals undergoing active stimulation and 14 undergoing sham. It's a very small data set. It's very preliminary data, but this is where we wanted to start to investigate whether we had value for predicting behavior using this dense array of information from current density. And so in this, we had some very clear responders and non-responders. About 7 individuals significantly in that active group improved, and the other 7 stayed pretty close to baseline and had very minor improvement, if any at all. And so classifying these using a binary approach for labeling and applying a support vector machine approach to this, we actually found that using this voxel-wise information across these individuals for current density, we could predict with 86% accuracy and 80% area under the curve who would, just based on the baseline T1, who would actually respond to treatment versus not. Now, this is not 100% fine, but I'll take 86% as a starting place in this small sample. We had k-fold, I think it was 10 k-fold cross-validation in this because it's such a small sample size, but this was a starting point. And let me unpack a little bit about what this told us very quickly. And really, it told us where in the brain was most relevant to these changes. And it told us that within the brain itself, there were some key characteristics of current that seemed to be most associated with treatment response. In those specific areas that were associated, more current delivered to these regions was associated with treatment response. Now, careful. Everyone wants to say more is better, and maybe that's true. But what I think of as more is merely different. More is more, but it doesn't mean it is better. We know that at this level of current, in this particular sample, this much current was associated with treatment response. That doesn't mean I could just double and triple the current and expect to find things got better. There's a ton of failed trials actually in the literature that tried exactly that approach. Well, 2 milliamps work, let's go to 3, and nothing works, right? We want to be more precise than that. We know that in this sample, for this outcome, these characteristics appear to matter. And that means if we know that, we can use that information. We can take that training data, we can take that T1 and a finite element model from the T1, we can train our classifier and come up with our optimal classifier solution for that data sample. And if we know where current mattered, and we know how much current mattered where, we can then, using, again, machine learning, deep learning, and other approaches, we can then impute into a new brain that we've never seen before, what is the optimized location of those electrodes and how much current to put through them to try to create that responder class field map, if you will, of current density. And so we've been chasing this for a while, and we recently published a proof of principle, which is just computational approach to this in brain stimulation this year. We took our finite element models, fed them through our classifier, identified, of course, what our optimized solution for treatment response was in that sample, and then took our non-responders from that sample and ran them through these computations to try to adjust their dose computationally to evaluate whether we could actually pull down the variation and actually make them look consistent to the responder profile we had found naturally within that sample. And lo and behold, at least computationally, we see that we're able to reduce the overall variation in the electric field, we're able to match up and actually beyond a 98% percentile probability the actual electric field map that was associated with responders and these folks who were non-responders. But this is computational, and that's fine, but we have to actually then test whether this in fact will work in humans. And so at present, we are in the process of running a small pilot trial that we will directly compare to the former trial we ran at a fixed 2 milliamp dose, same inclusion-exclusion criteria, same assessment measures, same recruitment methods, etc. But we're using our optimized dosing approach to try to drive this working memory outcome to directly assess whether we get improvements in functional connectivity above and beyond what was noted in that prior sample, as well as, and more importantly, behavioral changes above and beyond what we saw in that prior sample. This is just a quick snapshot of the montages that have been derived and the intensities that have been derived. We ran some early simulations within this sample because our sample data was only from 2 milliamps fixed dosing. There are ranges we can expect to reach, and 4 milliamps turned out to be about the range we could expect from that model data to have a maximum application of. With more clinical trial data, this technique becomes far more robust. At present, it is not generalizable, right? We need more data for that purpose to make it generalizable. We will see in this limited context, fun things here, you can kind of see that variation up above and below 2 milliamps, because again, we're trying to titrate that current to the responder profile for that specific brain. And so we'll see. We're not halfway there, about a third of the way there on the sample we're trying to recruit. And as soon as this hurricane gets out of the way, we'll restart our intervention sessions and get back to work. Now, I say, we need more data. Luckily, we recently finished in the past year a very large trial for TDCS and cognitive training. This was the ACTS trial, the Augmenting Cognitive Training in Older Adults trial. And in that trial, we actually collected data on 379 older adults undergoing active or sham TDCS and cognitive training. Now, the overall design was more complex, and I won't belabor because it was an adaptive trial design. But at the end of the day, we have a much larger data set to work with. 379 brains. Even with these automated modeling routines, what we did was go out and actually get a grant for secondary data analysis that will allow us, and in fact, we have just completed high-level 11 tissue-specific, high-fidelity computational models for every single brain in this study. We're actually in the process of error checking, cross-checking, and data quality checking. In the next 5 months, we will have the highest fidelity computational modeling data set on the face of the planet of the largest size. Now, it's older adults, so it's older adult specific, but that lets us go back into our behavioral, multimodal imaging, and a variety of other areas of interest within this data set and query at a more appropriate scale. I want thousands, but I'll take 379. We'll get there eventually as the field grows. But everything I've shown you to date is our preliminary work. We've got more to build on now, but as this field continues to grow, as we start to move toward finding and eventually find an FDA-approved clinical application, these are the kinds of techniques that we hope we can use to customize dose. But this is our first pass. I think there are very much other ways to customize dose. Not everyone's going to have an MRI system, right? But what's great about AI is, for example, CT scanners are widely available. There's some really cool work that's been ongoing to actually impute very accurate MRIs from CT scans collected in rural environments. We're not playing in that space at this point. My point is, with the various technology advances that are ongoing, we get closer and closer, even with something this complex, to potentially having a viable approach. But we've got a lot more work to do to really find how best to customize dose. Now, currently, we actually have, and it's under review right now, we replicated the basic effects of predictive value in our models in a sample of patients that underwent treatment for depression with TDCS in collaboration with Andre Brunoni at University of Sao Paulo. And we were able to actually generate a model that was 91% accurate in predicting, just based on their baseline T1, who would respond to TDCS treatment for depression. And so that paper hopefully will come out in the next 3 to 6 months. And we're actually working with Andre to design some new trials to try to leverage this and do proof of principle. The ACT trial, we have some recent findings and some new findings as we go through these data that are exciting. We're going to further explore, or in the process of exploring, including long-term independent activities of daily living improvements in the TDCS but not sham group. 3-month improvement that was quite significant, especially in those with premorbid anxiety at a clinically meaningful level, a reduction in anxiety in these older adults. We also found some very nice effects on depression, although clinical depression was exclusionary in this specific trial. We still saw very significant changes, not clinically meaningful because of the reduction in our range. So we've got some interesting findings to follow up. We have more data analyses underway. Our next steps, I'd really like to actually start moving further and further to the at-home application. I'd like to replicate some of these large anxiety effects in an at-home trial. Keep everything the same that was in the ACT trial, but run it entirely at home. Because in any good experiment, you change one thing. And the mistake in many cases in this field is people go in and change 5 things, and then no one knows why it doesn't work. Maybe we can't replicate. Maybe it was having people come in 22 times to see really nice people in my lab. We don't know. This will help us find out and build from there. We are planning for an initial anxiety optimized dosing trial, as well as a depression trial with Dr. Bernoni. And we would love to identify methods that are more accessible, more deployable, and can span more of the globe than a T1 weighted MRI. And because of the audience, I had to stick in at least a mention of FNIRS, who knows? But we would very much like to continue exploring this space and bring this closer to reality in terms of its dosing protocol, which gets us closer to getting this into the everyday world in a meaningful way. And there's not enough space in this slide to really thank everyone who contributed, but this is as many as I could fit on there. For the AI level work, Dr. Apunda Endalastari and Dr. Rogu Fong, in addition to my graduate student Alejandro Albizu, were critical and central in the overall AI elements of this. I don't consider myself an AI expert. I just play one on TV. These are the true AI experts who can answer all the really amazing questions. I know just enough to come up with crazy ideas, and they're the amazing, smart people that make them happen. And above and beyond everything else are funders, but more important than that are participants. None of this is possible without the many, many participants who spent their time and volunteered to work in our studies. So the biggest thanks goes to them, and thank you for your time.
Sure. Please come to the mic.
Adam, that was really impressive, really impressive. Thank you for the great talk. I have a question. You might have mentioned this, but I probably missed it when you were talking about the precision modeling, the modeling that aids the precision dosage. You did say that in your trial you've got varying levels of intensity, but I guess I missed what part of the model information is guiding that precision dosage? Is it individual anatomy plus current flow, or is it some combination of that? Like what is that information that drives the precisioning that you're showing?
No, that's a fantastic question. So it's literally current density and current direction at a voxel-wise basis throughout the entire brain. We know where we put the current in at. We know how much current we put through. And because of the T1 weighted MRI, we know the various tissue types intervening between those electrodes. Because we have a very good estimate from old physiology studies of the conductivity of each of those tissue types, we can solve the Laplace equation at each voxel to voxel, to really accurately estimate the current density and the direction of current flow that's highly probable voxel to voxel throughout. And it's that voxel-wise information, intensity, density, and direction of current flow that is feeding in that precision dose. So it's taking into account all those differences in adipose tissue or in skull thickness or any other number of factors that impact the flow of currents. And it's pulling that information in, but really driving it down to current density and direction.
So when a new patient comes in, I think that's what your trial shows. You don't know that information for that person. So does it sort of estimate what that person's individual anatomy would be like? So this is a good fit for that?
So we get a T1. So for example, in our current trial that we're running, they come in, we screen them, phone screen, in-person screen, they pass in-person screen. The next thing they do is come in for their baseline assessment with a T1. Right now, we actually worked with NVIDIA to speed our analytic processing. It used to take us like 6 weeks to do a single brain. It takes like 6 minutes now. And that's all NVIDIA and their snazzy hardware. But we actually take that T1 and we run that model. And that computational model is very automated based on a lot of work that's been done by others, but also us. And then we already know from our prior trials what our optimization solution needs to be. And really under the hood, it's running a variety of approaches to basically identify every possible electrode location we could put on that head and what produces the best match to the current profile we're trying to deliver to that person. Yeah, good question.
Hi, thank you for the talk. I was wondering if you think there's any effect of like daily fluctuations in anxiety and depression on how it's being affected with your treatment, and if you're thinking about implementing anything like EMA for those home trials to kind of get at what people's state is at during the treatment.
Yeah, I mean, I think day-to-day fluctuation in state is critical in many cases, and we gloss over this entirely and say, aha, at this one time point, your anxiety was the following, and that's all we use. And so this is where we've actually worked with a number of teams, and now with things like REDCap, what have you, we can actually do these daily assessments with individuals. Some of these at-home applications will actually build this into their portal where it's like they log in and it gives them a code for the day and they put their device on, and then it asks them a series of questions like the state trait anxiety index or what have you. And so, you know, with a mixture of trying not to oversample, right, but also trying to find that sweet spot of test, retest, I think the momentary assessments are huge. And the more we can find in domains relevant to this, yeah, it's going to give us new insight. We in this ACT trial, we actually recorded for every stimulation session, galvanic skin response, beat-to-beat heart rate variability, a variety of other physiological markers. We also have their daily performance, ups and downs in terms of cognitive training. We haven't even scratched the surface on those dense data sets, but a lot of the reasons we included some of those were for the same reasons, because using something like heart rate variability to get at cognitive efforts would potentially, for this day versus that day, maybe it has impact. And I think in the same context of what you're saying relative to anxiety, especially in these states that we're trying to alter, yeah, I think it matters.
Thank you very much for your amazing talk. And my question is about the future, the combination of the TDCS with another neuroimaging modality. So do you think any functional needs have any advantage and than using the EEG? Because an EEG, well, TDCS works on the neural network. So EEG would give you the neuronal answer, so which is more direct, and functional needs is kind of indirect because it deals with the hemodynamic responses. So do you have any opinion or expectation in this issue?
I do. We actually published a paper a couple of years back on the integration of TDCS and EEG. And we went in thinking, yeah, this is going to be fine. This is going to be great. And it was a total disaster. Because it turns out, if you're not very, very careful, you can significantly impact your data because of that passage of current. Now, we're detecting really small currents with EEG. We're putting in mass amounts of current, relatively speaking, using TDCS relative to what we detect in EEG. And then when we started doing this, and we were testing this, and I was up in New York with some collaborators, and we were working on this, and what did we see? We kept seeing what looked like this amazing 1 Hertz activity change in the data. And then we started looking closer. And it was a heartbeat artifact, because anywhere near where we stimulated, because of what it's actually doing to local blood flow, we actually saw a heartbeat artifact in our recording electrodes. Boy, oh boy, is that one tricky. You can factor it out. You get ECG and other information and do clever filtering. You can get rid of it. But without knowing that, it looked like this 1 Hertz spectral data was amazing. No, it wasn't. It was artifact. In addition, one of the things we know when we pass current through tissue is that we actually improve impedance in that surrounding tissue, which then really blows up my ERP studies, where I'm looking and all of a sudden, anywhere near that stimulating electrode, on the electrodes I probably care about to record from, it looks like I have huge changes in my ERPs. Well, it turns out, unless you're measuring moment-to-moment impedance and factoring that out of your data, which you can do, right, with very clever applications, that are far beyond my skill set. But as long as you're factoring this out, then you start to get closer and closer. So it is complicated. There are ways to do it. There's not any technologies, to my knowledge, that do this readily and packaged as of yet. In fact, there's a number of technologies that claim to do simultaneous TDCS and EEG, and they factor in none of the two factors I mentioned, not to mention others we identified. And so there's a word of caution there. I actually, and I'm not playing to the audience, I like the integration of FNIRS better, I think, in many ways. A lot of what we know from this is from fMRI and other approaches. And so for moment to moment, or even looking at closed loop based systems, I like the integration of technologies where the application of current won't interfere with the detection whatsoever of the signal, which is where a number of folks have become more and more interested in the integration of TDCS and FNIRS.
Thank you very much.
Yeah. Thank you.